Hi everyone. Myself Anchal. I'll be the TA. I'll be your TA for this course. As you all might have already enrolled in the course on power quality by Professor Bhim Singh. So welcome all of you to the course. And for this course, I will be the only TA that will be taking these tutorial sessions. And so basically, the purpose of this tutorial session is to bridge the gap between the NPTEL lectures that are available to you and the professor. So in case you have any doubts that are present to that occurs to you while attending those lectures and you want them to be clarified or discussed, then you can use this forum. So every Monday from 6 to 8, we'll have this session. Okay, and so I have a set of things that I'll be presenting today, but based on your input, if you want any other topic to be clarified, I can present it in the next session, depending on whatever the majority wants. So, if some of you wants to share your expectations from this tutorial, so you might have already seen few of the lectures present, right? So, if you have any kind of expectations different from what I have just mentioned, then you can just unmute yourself and tell me. So I'll just tell you briefly what I have prepared. So I thought of going through a brief revision of all the lectures that sir has covered in past 1 week. After that, I have prepared few questions, just numerical solutions, because when you solve the numericals, then you understand the theory also. So that is what I have prepared from my side. So if you have any other points or areas in which you would like any kind of clarifications, then please feel free to unmute yourself and just tell me. Okay, guys. So maybe you can you might be hesitant in the start. So I'll just start with the session for what I have prepared. And meanwhile, if you have any kind of doubt in between, then you can unmute at that point and ask on the spot, or you can post it in the chat box. If you have doubts related to some specific point in my presentation, then it's better to ask at that very moment. Okay. And I request all of you to please join at 6 dot so that we can start. Okay, because otherwise people will be coming in late and they won't understand what we are trying to do. So so myself, Anchal Singh, as I have mentioned. So I'm a PhD student at Interdisciplinary Center for Energy Research Department at ISC Bangalore, and I'll be taking your TA as I mentioned. So any kind of doubt, any kind of clarity you need, you can contact me. Okay. So I'll start this session with few tips from my side that I have learned. So even I was not from a top tier college, like I was not from an NIT or IIT, from a basic college. So after coming to IIC, I have learned a lot of things or mistakes that I was doing while studying. So before you start this course, I would just give you a brief. I'll just share those tips with you. So first and the foremost thing that I learned is connecting topics with the real world. So whenever you are studying anything, you can always find some connections with the real world. So like we are studying power quality, right? So you can look at capacitors, or you can ask people who are working in industry that what kind of compensation techniques are being used at their places. And also, you see capacitor banks. I think everyone who is in the field of electrical might have heard of capacitor banks. What rating of capacitor banks are put in those places, and so what rating of capacitor banks are put there, and why are they put there? How are they designed? All these things you can ask people, and then it will be you will get a very nice paralleling of the theoretical concepts that you are studying in class. And yes, the second point is equations. So because of the competitive exams that we have, we sort of have a mindset of remembering the equations, but that is never the way to go, because in electrical we have so many equations. So we should always try to derive every time a numerical comes, or every time a problem comes, try to derive it. So once you derive, that procedure will get set in your mind and you won't have to remember anything. So do revision. While doing revisions, derive things. And while revising, you revise in a flow. So it should be like a story, like, okay, the term is power quality. Why is power quality needed? Ask questions from yourself and then try to understand that why this is happening and why is it needed. So as many questions as you ask from yourself, you will realize that the flow in which any teacher is teaching a lecture has is in direct proportionality with the kind of questions you might have asked them if you have thought for the first time. So try to ask questions and then study any subject instead of just opening a textbook and then going with the topics one by one. Okay. And next, I would say that try to understand results. So whenever we solve a numerical, we just get a result and then we end there. So don't stop there. So there will be multiple numericals in your assignments, right? Part one, part two. So try to understand the significance of difference between the results. So in one question, they have asked you to calculate losses, right? Losses without compensator. And in another one, they have asked you to calculate losses with compensation. So try to understand the difference in those two scenarios. Okay. So if you do that way, then you will be able to understand better. Okay. And next is simulations. So I am parallelly using MATLAB editor to design script for calculating these sequence components and the reverse, and then in order to ease my time using calculator. So you can also parallelly write MATLAB scripts. We can discuss them here if you want. So I can show you the MATLAB script that I have written. If you want, I can share it with you, or we can, and later on you can do some simulations on Simulink. So sir has used a lot of basics from power electronics. Like sir has used the rectifier circuits, DC to AC converters, and inverters, and three both single phase and three phase. So all these results, if you already understand, so you will be able to understand the actual points sir is trying to focus in the lectures properly if you already have those basics in place. And in case you have doubts in any of those, you can use Simulink for simulations, and you can ask if you want it. I can also present if you want. Okay, and then next is, yeah, you can always discuss and ask any kind of doubts. So I this is my second time volunteering for these lectures. So I've already done that with one of the course. So these sessions become much more effective once you guys start talking to me. So don't be afraid. Don't be afraid about asking any kind of doubt. So next point is, no doubt is stupid. So just feel free to ask. Okay, as ask as many. No, don't think whether your question is stupid or not. No question is stupid. Just ask, and I'll be happy to answer that. And if I get to interact with you guys, it will be a much more interactive session. So that's what I wanted to tell you guys. And then before moving to the numerical problems, I will just go through a brief revision of what has been taught to you in previous sessions. So all these documents, whichever I am sharing, I'll be putting up all these documents in the folder. So I think NPTEL has already given you the links. So all these all the lectures that is taking place right now, every lecture for 12 weeks will be put on the YouTube. So I'll be putting the link. I'll be sharing the link with NPTEL people, and they will provide you with all the links and all these documents which I am using for presentation, for revision and for the numericals that I'll be solving, all that PDFs I will put in the folder. That link also will be shared by NPTEL to you guys. Okay. In case you need anything extra, you can just let me know. At the end of the lecture, I will show you the MATLAB script that I have written for for making the calculations easier. So you can try doing that if you are interested. Okay, so we'll start with the with what sir has covered in the lectures, a brief review of what you have studied in the first week. So the course title is Power Quality. So the term power quality, all of us knows that it refers to assessment and maintenance of good quality of power. So what is good quality of power? So everything has certain references, right? I don't need if I have 100 rupees, I will try and I need a purse. I will try to buy a cheaper purse. If I have 1,000 rupees, I'll try to get a better quality purse. So all of us use this term quality in daily sense, right? In daily use we use this term. But when it comes to power, so this is not a very popular area. The reason for this not being a popular area is that it was not needed so far. So if I ask you what is the quality of power that is coming to your house, then you will say that the power that is coming to your house is then you will see that the power that is coming to your house has this such and such voltage rating. So if 230 volt is the exact rating, you will say that the voltage in my home comes in the range of 200 volts to 230 volts. And you will just know that. You won't know anything else, right? You will know that there is some itne units consumption I have done, so I have to pay this much bill. That is the only thing you know at consumer end. But there are a lot of other parameters at micro level that your energy meter does not measure, right? So the only thing that you measure at your house is the voltage. You are able to see instantaneous value of the voltage, RMS value of the voltage you are able to see, and apart from that you are able to see the power factor. Okay, so when these people come for billing you, so if in industries, if your power factor is less than certain is below a certain level, then they charge you penalty for that. And why did they do that? Because of that power there is a lot of pollution. So when I try to think of power quality, I try to think of in terms of pollution. So we all know air pollution, right? It is very common. So we have electrical pollution. Analogous to air pollution, we have electrical pollution. Now, what happens in electrical pollution and why it happens? So initially, all of us know that the kind of power that we wanted to consume was simple sinusoidal, right? We all wanted simple. This is what we desire in electrical. We all have studied, right? Why we desire sinusoidal kind of current or sinusoidal kind of power. So when your power is sinusoidal or the waveforms are sinusoidal, then you are able to draw and in phase. Suppose this is my current waveform and this is my voltage waveform. Okay, then both of them are in phase, and in this scenario I'll be able to draw maximum power, right? So because of this situation, since I'm able to draw maximum power here, that is why I always desire my system to draw sinusoidal power. But nowadays what is happening is my the nature of the current that I have is no longer sinusoidal. It is having different shapes. Like we have you all might have studied thyristor circuits, right? The current will be like this, like this, like this, or uh, or it will be like this, like this, like this, or it will be very bad, like it will be literally peaks, pulsating current, right? So all these kind of waveforms, what is happening is it is very different from what we wanted, like the sinusoidal, which is the ideal kind of current that I want to draw from my system. Because of these nature of current, if I think all of you might have heard about Fourier series, right? So when I break down these waveforms into Fourier series, so what is Fourier series is an cos n omega t plus bn sin n omega t, right? So so using these Fourier series, you are able to break down these weird current signals that you don't understand in terms of sinusoidals. Sine and cosine you understand, and you want your current to be as similar as possible to sine and cosine. But these are very different. So we try to break them down into what we know. We know sine and cosine, and we don't know these weird current waveforms, right? So I'll break down these weird current waveforms into sine and cosine terms. And once I have done that, I will realize that these currents are very different from the sinusoidal. And because of that difference, because of what is left, because of what is left when we are not having sine and cosine waveforms, then what we obtain i- is called harmonics. So basically, harmonics is one kind of pollution that I'm talking about. Then apart from that, there are a lot of other kind of pollution. So you can understand power quality in terms of pollution. Okay. So now because of nowadays all the so initially we used to have incandescent bulb, right? Simple incandescent bulb we used to have, and
होता
then
ना वो अच्छे
uh,
हैं
we started having LED bulbs, right? Incandescent LED bulbs. Now, any of you know why have we moved from incandescent bulbs to LED bulbs? We all know that it is saving, it is something good is happening. We all know, but what is changed? So what happens is when we move to LED bulb from incandescent bulb, our power consumption has reduced. For the same amount of lumens, that is the unit of light, for the same amount of lumen, if I required 10 watts of power before, for LED bulbs, I just require 5 watts. Just say, just for per se, on per se basis. So I require only very less power now compared to what I needed before. So because of this saving, everybody has moved to LED bulbs, and we can't find incandescent bulb anywhere nowadays, right? So this is the reason. But what is the cost of this power saving? Because of this power, because in order to get this power saving, we are paying the price in terms of grid pollution. So the LED bulb, the incandescent bulb used to draw sinusoidal current, but LED bulb does not draw sinusoidal current. The kind of the current that it draws is one of these currents. So because of the bad current that LED bulbs draw, power quality problems in the grid increases. Okay, so since we are moving to more and more those kind of devices which have power quality problems. So because of those power quality problems, the importance of this area has increased. Initially, we were using devices which would be very much compatible with sinusoidal, but now we are the currents drawn are no more sinusoidal. They are non-linear in nature. They are weird shaped currents. So because of those weird shaped currents, and why are these weird shaped currents coming? Because we are using more power electronic converters, right? Nowadays, any system you open, be it your washing machine, your refrigerator, any kind of appliance, you just look around your home and you will find that it has power electronic converter embedded inside that. And then we all know electric vehicles, right? Electric vehicles are coming. So we are charging those electric vehicles, and all of us want fast charging. So because of that fast charging, what is happening is you are drawing huge amount of power in very less amount of time, right? That means you are giving indirect, in a way, you are giving a very big surge to the grid. Okay, so if you want large amount of power in small amount of time, you will again start drawing these peaky currents which we were talking about, right? This will be the kind of current that will be drawn when you are using EVs. Okay, so because of these EVs, then there is distributed generation, right? Now, what is distributed generation? Because of solar, wind. So wind is not used that much at consumer level, but you all might have seen solar panels. Okay, so solar panels at your friend's house everywhere. So because of these solar panels, what is happening is the nature of the power that solar panels give you is something like this. Okay, so the peak power is at 12 noon. So from say 6 a.m. to 6 p.m. This is the only time during which you get power, right, from the solar. Is the power curve. So this is the only time during which you get the power. Rest of the time during night there is no power from solar. So because of this intermittent nature of solar, and when the cloud comes, so in a city like Bangalore, Bangalore is very cloudy. So when there is cloud over the panel, when there is dust over the panel, any kind of any these kind of situations, what happens is the power generation by these solar systems vary. So because of this varying nature, what is happening is sometimes solar is giving, sometimes it is not giving. So because of this intermittent nature, the nature of electrical loads that are connected to our grid. So if we have this source and if we have this load, so initially our load was very much fixed. It was not it you can call it sort of static load. It was very easy to predict the nature of load because I know that I have a five incandescent bulb at my house. I have one TV. So it was very much predictable that this is the electrical consumption. Our electricity bill used to come almost constant. But now with the nature of this load, what is happening is because of these kind of loads, the the load is changing dynamically, and because of this dynamic change in load, we have to take care of power quality. Otherwise, if not taken care, then there would be lot of problems. There might be cumulative problems that we'll discuss later. So that is the reason that power quality has become one of the most important areas in today's scenario, and a lot of exciting areas will come up in connection with this power quality area. So you have taken a good course that way. Okay, so the basic traditional definition of power quality is it is generally referred to assess and to maintain the good quality of power at the level of generation, transmission, distribution, and utilization of the AC electrical power. So there are four stages in which power reaches to you. So at suppose synchronous generator is generating the power that you are getting at your home. So there will be generator end. Then from generator, power will suppose voltage rating at generator end is 11 kV. Then in order to transmit the power efficiently, I will scale it to say 66 kV. Then 66 kV power at 66 kV will be transmitted. Then it will come to distribution transformer near our homes. So then I will scale it down to 11 kV. Or and then in the nearest transformer to to your house, this 11 kV will again be scaled down to 400 volts or 415 volts, and that is the power that you receive at your homes. So there are four levels: generation, transmission, distribution, and utilization. Out of all these four levels, the maximum pollution occurs at utilization level. Why so? Because because you have this source again. This is the source, and this is the load end. So what is happening is the nature of load is varying. Source is trying to supply the best kind of and the ideal current. So the source current that is supplied is ideal. That means it is sinusoidal. They are not giving any kind of the current that they are trying to send to us is nice sinusoidal. But the current that our load is demanding, that is bad or with the polluted current we can call it. Because of this bad current, what is happening is this source also is impacted. So our load is the major problem. So in power qual in so when we say that we want to improve power quality, if this is the source where my problem is arising, then I will try to solve it here itself, right? I will not try to, if the problem is at load end, I will not try to solve it at the source end. It is much more efficient to solve my problem which is arising due to load at the load end, right? So that is why whenever we talk of any kind of power quality improvement technique, that is mostly applied at the load end. Okay. Now, so there are a lot of reasons for the pollution of grid. Yes, somebody has raised the hand. Yes, can you please unmute yourself and ask? Guys, in case you have any doubts, please don't raise your hand. You can directly unmute and ask. I can't see here who raised, but in case you want to ask anything, please feel free to unmute yourself. Okay.
This session recording will also be available, ma'am.
Yes, ma'am. You will get the recording of this session. A link will be shared with you from the NPTEL people. All the documents that I'm using that
Hmm.
will be uploaded to the drive, and that link along with the YouTube link will be shared with you.
Okay, thank you.
Okay. Okay, so we'll move on. Yeah, so we were talking about the grid pollution, right? So we understood that the maximum pollution that is obtaining in the grid will be at the level of utilization. Okay. Now, what are the causes of this pollution? We already sort of discussed few causes, but let's see the categories. So they can be majorly classified into natural causes and forced causes. So natural causes constitute 60% of the total causes, and forced ones are 40% only. So what are the natural causes like lightning, flashovers, equipment failure? Because of the lightning, lot of lightning, raining, luckily, we don't have snow in India. Otherwise, in foreign countries, because of the snow, maximum damages occur in foreign countries during the time of snow because the snow sits like it accumulates on the wires, transmission wires, and it breaks the like the wires are at a very stressful condition during that situation. So natural causes are the major ones, and equipment failure is also a natural cause. Faults are also a natural cause. Then forced ones are 40%. Forced ones are like voltage distortions, notches. So if you are connecting a bad kind of load to the grid, it will come into the category of forced ones. Okay. Now power quality problems. Now power quality problems can be have a lot of categories. So there is no I cannot there is no fixed number that there are 10 kind of power quality problems. There are a lot of power quality problems, and with time I think they will keep on increasing because our nature of load is becoming very dynamic with time. So the basic in order to classify power quality problems, we take voltage and current as the class in order to classify them. So these are the basic parameters. So in electrical, whenever we talk about there is voltage, there is current. These are the fundamental parameters. All other parameters, active power, reactive power, power factor, all these are derived parameters, right? So these are the fundamental ones, and these are the derived parameters, right? So there are only two kind of fundamental parameters. So in order to classify power quality problems, we have classified them in terms of the fundamental parameter with which this power quality problem is associated. So when I talk about voltage as a fundamental parameter, then there are voltage harmonics, voltage surges, notches, all these problems when they are associated with voltage parameter, then they come in the category, then they come in this category. And when these problems are associated with current fundamental parameter like current harmonics, excessive neutral current, and unbalanced currents, then all these parameters come in the category of power quality problems that are associated with current. Okay, so these are the basic qual classifi quali classification of power quality problem. Okay. Now, as I mentioned, I'll be discussing the impact of these power quality problems. So, as you can see, I have taken two power quality problem here, unbalance and harmonics. Okay. So, because of unbalance, what is happening is I am not able to use my grid to its full capacity. So, what is happening is, suppose I have three phases R, Y, and B. Okay. Now, because of unbalance, if my R phase is having 20 ampere loading, Y phase is 5 ampere, and B phase is 5 ampere, then what is happening here is if I try to connect a three phase load, if the maximum capacity of this three phase system is 20 ampere, okay. Now if I want say 25 amperes, okay. Now if I want to connect a three phase load of 5 ampere per phase current, then I can okay, okay, if I want to connect a three, I have a three phase load, okay. Okay, okay, this is my three phase load, okay. Now this load needs 10 ampere, okay, 10 ampere per phase. Now I will not be able to connect this to my system because R phase will be overloaded in that case. But if this system would have been balanced, I would have been able to connect it. So because of this unbalance, although my Y and B phase are lightly loaded, I could have easily connected it. But because of this unbalance, I am not able to connect. So that is the problem with unbalance. So I am not able to, hence this point, and an inability to utilize the grid to its existing capacity. And then there is misfiring of protection equipment. If the moment I try to connect this three phase load to this kind of loaded electrical grid, then my system will trip, which was not actually the case. My Y and B phases has the capacity, but still my system tripped because of this unbalance. Now, because of the unbalance, the power supply quality degrades, which impacts the operation of load and reduces the life of loads. So we most of us don't realize this because it happens over a long period of time. So if I have an electrical pump, all of us have tanks, right? Water tanks at our houses. So in those water tanks we have motors, right? Pump motors. So if we don't give power supply with good quality to that motor, then its life reduces. If I would have taken my motor and I have given it good quality supply, then if it would have worked for 20 years, then if I won't give good supply, if I give bad or polluted supply to the motor, it will not work for 20 years. It might work for 10 years only. But we don't realize this because we think that 10 years are also sufficient. So we don't know these things. That is why awareness about these area is also very important. So this is the impact of this is the major impact, and this is the major reason why power quality has become very much important. And once user become aware, they try to switch to that kind of electricity provider which have better power quality. Then because of unbalance, saturation of distribution transformer lot of time takes place. So you might have very frequent electrical cuts. So because of the reason for those electrical cuts is the saturation, the very frequent, the most kind of majority faults occur at distribution transformer. And distribution transformer is the one equipment that is very costly, and that has the major cost that is required. It consumes a major cost of repair and maintenance in electrical distribution system. So the unbalance plays a role in damaging or saturation of distribution transformers as well. So then when we talk about another power quality problem, say harmonics. So because of harmonics, we losses occur in the grid, and because of that losses, system's overall efficiency is reduced. And because of the losses, I have to give more power to the system to supply the losses also. If ideally my system had 20-watt rating, but it has 5-watt losses, so instead of supplying 20 watt to the system, I will have to give 25 watts. 5 watt additional I have to give to supply to the losses. So that is the problem with harmonics. And because of harmonics, if you talk in case of machines, then in machines, lot of because of this presence of harmonics, lot of heating takes place in the machines. And heating is a devil when you talk about machines or any kind of electrical equipment. Okay, so because of this increased kVA demand, our power factor reduces. So these are just two power quality problems that we had focused so far, and you could see, how this has a growing impact. So that is so if you try to make such diagrams or trees in order to connect the power quality problems to their causes, then you will be able to understand it rather than remembering. It will be easy for you to remember these things. Then sir has talked about power quality standards. So when you say that there are power quality problems, and then there are you have to improve the quality of something, you have to give some reference, right? So when we talk about food, okay, then we say that my food should be approved by FCCI, okay. And when I try to buy an equipment, then I'm going to use it outdoors, then I say that it should have an IP rating of above 65. That is the most rugged available. These are all the standards or the common references that we talk about in our day-to-day lives. So similarly, for power quality also we have lot of standards. So since there are a lot of standards, then the question comes is which one to follow, right? So there are two main agencies that are generally followed by the majority of the commercial as well as academic players. One is IEEE, another one is IEC. So IEEE is Institute of Electrical and Electronic Engineers, and IEC is International Electrotechnical Commission. So both of these agencies uh, produces standards depending on time. So whenever they need some kind of amendment, then they issue a new standard. So a lot of standards are present, and Sir has given a list in the lecture. So you can just go through one of them. Sir has marked two, three main two, three main standards. So you can just go through, even if you're not reading it, just go through it. Have a glance at it. That what are they telling? So in standards, normally what they do is they tell you that if you are okay, if you are a user, if you're a industrial user, then you cannot pump third harmonic current above 5% or fifth harmonic current about 2%. All these kind of regulations are being imposed in these standards. Okay, so you can just go through them, you will get an idea of what exactly. So whenever suppose I want to open my company and I want to make an electrical equipment, then the equipment that I make has to follow these standards, because because in order to get the certification for the equipment, I'll have to go through all these tests. So my equipment will be the third harmonic current of my equipment, fifth harmonic, all these will be measured and they will be checked corresponding to the standards that are present in these by these agencies. So until and unless I pass that criteria, I cannot design any equipment of my own. So that is why these standards are important. And these standards, so these both are international. One is IEEE is mostly followed in US, and IEC is followed in mostly Europe area. So these are two major ones, and the standards that are imposed by government, they are different for different states. They are variable depending on states. Okay, so you can check that out. Now next is custom power devices. So now we know that power quality problems are there. We have already seen, right? Now, now we need to solve these problems. So in order to solve these power quality problems, there are few equipments that are available in market. So few of these equipments are DVR, that is dynamic voltage restorer. It solves problems. It it solves problems for the problems that are present in series in the network. So voltage problems mainly. So if you have if you have power quality problems with voltage as the fundamental parameter, then you can use DVR, that is dynamic voltage restorer. Then there is DStatCom, that is distribution static compensator. Yes, Anil sir, you can ask your question. Whoever has any doubts, please feel free to ask. You can just unmute yourself and ask, okay? So DStatCom is a shunt device. It is used to solve power quality problems with a base parameter as current. So whenever I have a current based power quality problem, I will try to solve it using DStatCom. And UPQC is a hybrid. It is a combination of uh, both series and shunt circuit. That means it can solve both series and shunt power quality problems. That means power quality problems associated with both current and voltage can be solved using UPQC. So UPQC is uni- Unified Power Quality Conditioner. Okay. Now we have already discussed about the incandescent lamp versus LED bulbs, right? For the same amount of lumens, I am consuming less power with LED bulbs, but the price I am paying for this less power is that my power quality problems have increased because it is consuming non-sinusoidal current. Okay. Now, state of the art in power quality. So, as we have also discussed that in recent areas, in recent times, power quality has become very important because because of the nature of loads, electrical loads that we are having in our homes. All the loads have front-end power electronic converters in them. Our washing machine, refrigerator, embedded system, toys, everything has power electronic converters in them. So because of that, the nature of current that we're consuming is not sinusoidal and it is very non-linear in nature, because of which we have increased power quality problems. Then apart from that, there is a distributed generation, that is solar, wind, because of the nature of this generation, which is intermittent in nature. Sometimes in it is present during the day and it is absent during the night. Because of that on and off and variation in load, distributed generation, because of this also the nature the power quality has become a very important area. The next is deregulation of power supply. So what is deregulation of power system? So what happens here is, so initially there was only, you can call it a monopoly, right? There was only government who were responsible for supplying electricity to us. But nowadays, uh, after the Deregulation Act a few years back, government has started giving out private companies this task. So in Mumbai, especially, there are a lot of options for selection of power. You can take power from Reliance, or you can take, I think, Tata. Yes, Tata is also there. So you can choose which company's power you want, right? So now when there are multiple competitors, initially you didn't had any option, right? Only government can supply. But now you have multiple players in the market. You can take from Tata or you can take from Reliance. So now, in order to compare between them, you need something, right? You need some basis. So then power quality again becomes an important parameter. So you will say that Reliance power is off has a lot of off period. That means it gets cut. It has, in 1 month it has cut 5 times, and you will say that Tata Power has cut only 2 times. So you will try to go with Tata. So that is continuity of power supply. That is also one of the areas of power quality. It comes with power quality. So this power quality area gives you a basis, right, of comparing between multiple companies in the area of deregulation of power systems. Then sir has discussed classification of power quality problems. So power quality problems has lot of basis for classification. So based on the events, they were classified as transient and steady state. So transient means short, for a short period of time, and steady state means even after they exist for a longer duration of time. So transient is for like small interval of time. Like if I'm turning on a system, okay, then that will be called as transient. But if I have turned, now my system has turned on and it's been 5 minutes after turning on, and now also some kind of problem is present in the system, then that will come in the category of steady state, right? Then another classification of power quality problems is based on the base quantity that we have already discussed. So far we have discussed the power quality problem related to voltage and current, but there are power quality problems related to frequency and power factor also. Okay. Yes, Dinesh sir, I got your message. All these documents that I'm using and the recording of this video, they will be shared with you. Okay, in the on the NPTEL portal, they will provide you the links to both the documents as well as the video lectures. So this will be uploaded on the YouTube. Okay, so you can access from there. Okay, welcome. So then sir has discussed lot of power quality terminologies. So you can so if you can parallelly try to see waveforms in order to understand those terminologies better. Okay, and then sir has gone through a lot of numerical problems, and so are we are also going to do the same. So I'll be solving a few numerical problems. We'll be doing them together. So as and when you have any other doubts while solving those problems, you can stop me in the between. Okay, so the whole purpose of doing this while you having online is so that you can ask me doubts. So try to make the best use of this thing. Okay. So I've prepared few problems. They are not exactly your assignment problems, but you can get a lot of help while solving your assignments. Okay. So first problem is a three-phase balanced supply system having phase voltages VA equal to 0.9 angle 0, VB is equals to 1.1 angle 240, VC is equals to 0.95 angle 120 per unit, has unbalanced load currents. So the supply voltage is balanced, but the load currents are unbalanced in this case, okay? And why are they calling the supply voltage balanced? Because the angles are balanced. And in load current, they are calling it unbalanced because the angles are not balanced. So one IA is 0.75 angle minus 120 degree, IB is 0.65 angle 270 degree, and IC is 0.35 angle 90 degree. So, and in the question, we are asked to find total complex power in per unit. So, since all the parameters are already given in per unit, I don't have to make any conversions. And then they've asked us to find the total complex power. So, we all know that total complex power for a three-phase system, be it balanced or unbalanced, is given as VA-IA conjugate plus VB-IB conjugate plus VC-IC conjugate, right? And we have all these parameters available with us. So VA is 0.9 angle 0, IA is 0.75 angle minus 120. So its conjugate will be plus 20 degrees, right? So I'm directly taking the conjugate and writing. And then VB is 1.1 angle 240 degrees and IB is 0.65. After taking conjugate, it's minus 270 degrees. And then VC is 0.95 angle 120 degrees into IC is 0.35 angle minus 90 degrees because of the conjugate, right? So when you solve this, it will come out to be 1.541 plus J times 0.0396. This is in Cartesian form, and in polar form also I will write 1.542 angle 1.47. Okay. So this is our total complex power, right? And as we know that S is equals to P plus JQ, right? This implies, not asked, but still 1.541 per unit. So remember the units, right? Okay. So this is the total complex power that was asked to calculate, right? This is the expression, right? Now this was a balanced voltage system and unbalanced current system. Now in the next problem, they have given us unbalanced voltage and unbalanced current. And we are asked to find the positive sequence component of power. Now, for a since we have to find the sequence components now, so I'll just write the matrices that I'll be using for sequence component once, and then I'll use them from next time again. Okay, so you can just note them down. So A, B, C are the parameters, and it could be voltage, current. It is same for both. So A, B, C are the three-phase parameters. Then I'm writing it in the matrix form. And A0, A1 and A2 are the sequence components. A0 is the zero sequence, A1 is the positive sequence, and A2 is the negative sequence. So this is, and I will write its inverse also. And from the next time, I will directly use it in all the numericals. So you can just note it at one point, and you all should know the derivation of this one, right? It is very simple derivation. In case you have any doubts, we can discuss it. Okay. So now we know that total power is VAI conjugate plus VBIB conjugate plus VCIC conjugate. which is equal to when you use these matrices and convert these phase quantities into sequence components, then you get these equations. So this additional factor of 3 comes when you convert these matrices. If you can try this derivation as well, it is a very simple derivation. You just have to write the expression for apparent power S in matrix form, VA, VB, VC, IA, IB, IC, and then just use these matrices, these equations that we just obtained. Okay, so when you use these equations in order to convert these phase parameters into sequence parameters, you will obtain this equation. You will be able to obtain this equation. Okay, you try this time, and if you're not able to get it, then we can discuss it in the next class. Okay, just you inform me what clarifications you want, and I'll be able to give it present it to you. Okay, so now we know that this is the component of apparent power corresponding to the positive sequence, right? So when asked, so I'll be so S1, let me see the component of apparent power corresponding to positive sequence as S1. So this is 3 times V1 I1 conjugate. So V1 I1 are positive sequence component, V0 I0 are negative zero sequence component, and V2 I2 are negative sequence components, right? So 3 times V1 I1 conjugate, and then V1 and I1 ka expression I can obtain from the matrices is 3 times. V1 is 1 by 3 VA plus A times VB plus A square times Vc. This is V1. And then I1 conjugate, which is 1 by 3 IA plus A times IB plus A square times IC conjugate, right? So when you can directly put the values, right? I'll just write the expression directly. So S will be equal to 1 by 3 times. I'll write one intermediate steps in case you have some calculation mistakes. 0.9725, and then then I conjugate part is 2.1298 angle 6.975, and this is conjugate. This is V1 and this is I1 and it's conjugate, right? So when you solve it, you will get 2.0914 angle minus 7.89. Okay, so this is the S1, right? We were calculating S1, which is equal to 3 times V1 I1 conjugate, right? So let us move on to the next question. So in problem 3, a single phase uncontrolled bridge converter has RE load with R as 1 ohms and E as 290 volts, and the input AC voltage is 230 volts and 50 hertz. Feeder conductors have a resistance of order 0.05 ohms each. We need to calculate the AC supply RMS current in amperes. It's a single phase. And the nature of load that is connected is RE, right? Where E is 290 volts and R is 1 ohms. And this is supply voltage, this is supply current. And these are the feeder conductors, right? This feeder has, each feeder has resistance of 0.05 ohms, right? per conductor. Now, these kind of numericals, I like my way is to always make the waveform first in order to understand, because there are a lot of formulas when it comes to these converters. Okay, so always try to understand this with the help of waveforms. So if I say that the supply voltage, which is 230 volt 50 hertz, so suppose this is my waveform for the supply voltage. Okay, so since it is 230 volts, the peak value will be 230 into, it's a sinusoidal, right? So the peak value is 230 into root 2, which is equals to approximately 325 volts, right? And they have given me that E is equals to 290 volts. So I will take this as E, okay? So this is E, which is 290 volts, okay? Now I need to draw the waveform for IN. Now, if you look at the system, so when I have a positive half cycle of Vs, in positive half cycle of Vs, I will just name the diodes. 1, 2, 3, okay. Yeah. So in the positive half cycle, what will happen is D1 and D4 will conduct, right? So once D1 and D4 conducts, my circuit will be in positive. So the supply voltage will come across R and E, right? It will be a direct connection, right? And in negative half cycle, again, it will be a direct connection. The only thing is, if this is the positive, this is the direction of IS, then during negative cycle, we are talking about positive and negative half cycle of Vs, right? So during negative cycle, what will happen is the direction of current will be this, and this will be R. Yeah. So the circuit will remain something like this. Okay. So we'll realize that when so these are this resistor R is connected between, in both the cases, in positive as well as negative half cycle, the circuit is, the resistor R is connected between the AC voltage Vs and that E voltage, DC voltage source E, right? So the current will flow only when one voltage is greater than the other, right? In other case, since this is an uncontrolled circuit, power can flow only from AC side. This is AC side, this is, let's say, DC side. Then power can flow only in one direction because it is uncontrolled. Only diodes are present. When power will try to flow from DC to AC, these diodes will get reverse biased, right? So the current will conduct only when Vs is greater than E, right? In this circuit, from both of these circuits, I can clearly say power flows from AC to DC only when Vs is greater than E, right? So from this diagram, I can clearly mark the regions in which Vs is greater than E, right? So these are the points at which Vs is equals to E. So in order to find, we need to find this angle, right? So we will have to, later on, we can find it using the condition Vm sin omega t is equals to E. And omega t I am calling here as alpha. So using this condition, you can find the value of alpha. So these intersection points will tell me when will current flow, right? So during these periods, these are the only periods during which Vs is greater than E. And since during these periods Vs is greater than E, therefore during these periods only my current will flow. Let's say my current has some this kind of waveform. Okay. Now I am asked Now I have the waveform. I know how to calculate RMS value, right? The basic formula. So I know that I have this signal and I have to calculate its RMS value. So in order to calculate the RMS value, you will need this angle alpha, right? And then this is exactly symmetric, right? This is pi, this is 180-degree pi, and this is pi minus alpha. So this point is alpha, this is pi minus alpha. So in order to calculate the RMS value, I need alpha and pi minus alpha points. So in order to calculate alpha, I'm sorry, yeah. So in order to calculate alpha, I already know this condition. So I'll just take this condition in the next page. So using the condition that I'll just connect it using equation 1 that I just marked there. So in that equation, what we have seen is at this point of intersection, right? At these point of intersections, Vm sine omega t is equals to E, right? Vm sine omega t is equals to E. And I'm calling the omega t or the angle as alpha because I want to find it. So Vm sine alpha is equals to E. This implies alpha is equals to sine inverse of E by Vm. So Vm we know it's 230 root 2 and E is 290 volts. So using this, alpha comes out to be 63.07 degrees. Okay. Be careful of the units degree and radians whenever you solve any kind of numericals. Now I know the formula for RMS of any kind of quantity. So the supply RMS current will be equal to 1 by T. Okay. So I need the now I need the expression for the supply current, right? I know the limits alpha and pi minus alpha. So from these circuits, you can directly write that from these circuits that Is is equals to Vs minus E by R in both cases, right? Only Vs, the Vs, you can write a general equation, right? So if I write Is is equals to Vs minus E by R and Vs is equals to Vm sine omega t and E and R are constants, right? So I can just put this value in this expression. So the time period for this clearly from the waveform, this is repeating in 2 pi interval. Just 1 minute. Yeah. So yeah. So this is the time period, and then it will be Vm sine omega t minus E by R square d omega t, and the limits will be from alpha to pi minus alpha. I hope you don't have any problem solving these equations. In case you have any doubts in these, then also you can ask, okay? You just put the square, a square plus b square expression, expand it, and then integrate the individual terms. So I'll write the final expression that you will get while doing this. Square by 2 plus e square into pi minus 2 alpha plus Vm square by 2 into sine 2 alpha minus 4 Vme into cos alpha. So you can just put the values of these parameters, and R, which is the resistance, will be R, which is the total resistance. So we have load resistance of 1 ohm and then 0.05 for the feeder resistance, and both two paths are covered, right? So this is one path, and then there is this another path, right? So both of for these two, I will multiply 0.05 into 2, right? 0.05 will be multiplied by 2. So hence the total resistance will come out to be 1.1 ohms. So R will be this. Vm we already know, 230 root 2. E is 290 volts. Then alpha, in few places you have to use it in degrees, and in few places you have to use it in radians. Okay, so just be careful where here it will be in radian, and then an argument of sine or cosine it will be in degrees. Okay, so be careful of about these things, right? So IS RMS will come out to be approximately 12.7 amperes. Okay, you can use these numericals for practicing. Okay, and you can resolve them on your own. And if you have any doubts, then you can ask me in the next session. So as a part of the same question, they have asked us to calculate the fundamental RMS current in amperes. So in this case, the current that was drawn is not sinusoidal, right? So it will have, when we break this current waveform, this green waveform. So when we break this current waveform into sines and cosine parts of it, then what we'll realize is that it has both sine and cosine components, right? So it will has fundamental as well as harmonics along with it. So if we want to calculate only the fundamental part of this current, then what will be the value of that current? Only the fundamental. So in order to calculate that current, what we'll do is we'll go approach this problem from the load side. Fundamental RMS current will be the current which is responsible for the active power. So fundamental RMS current will be equal to the output power of the system by Vs, which is the source power. Okay, so now I need the output power that is going to the system in order to calculate the fundamental RMS current. This is one way. Another way could be finding the Fourier series, and then you can find the Fourier, the fundamental component as well. But this is, and I feel that is the easier way. So in order to calculate P, that is active power drawn from AC means is equals to ISRMS square into RT plus E times I average. So since for resistor I will use RMS current, and for voltage source I will use average current, right? So this is a standard formula for active power. Okay. So now I have RMS current, but I don't have average current. So I'll have to find the average current. 1 by T integral from alpha to pi minus alpha, right? We found the limits. Then it will be again Vs minus E by R, and Vs is Vm sine omega t minus E by R. T omega t. So this expression, when you solve it, it will come out to be 1 by pi r 2 Vm cos alpha minus E times pi minus 2 alpha. And when you substitute the values, R is equals to 1.1 ohms, we just calculated in the previous question. Vm is 230 root 2. Alpha is 63.07 degrees. And in radians, it is 1.1 radian, right? So I average will come out to be 6.24 amperes. Okay. Now we can calculate P, which is equals to IS RMS square into RT plus E times I average. So this will be, that current was 12.7 in the previous question, right? I RMS square into RT was 1.1. 1. E is, we all know, 290 volts. I average is 6.24 amperes. So this power will come out to be 1987.019 watts. Okay. And now fundamental RMS current equal to P by Vs. P is 1987.019 by Vs is 230 volts, right? This is watts. This will give me the fundamental RMS current, which is equals to 8.639 amperes. So this fundamental RMS current should be less than the overall current that we calculated. So initially the total RMS current is 12.7 amperes and this is 8.6. So rest of the current, the difference between this current and that current as is going into the waste harmonics, right? So this is how, as I mentioned, that you can connect all the answers that you're getting. So if this value would have come out to be 15 amperes, I would have been suspicious, right? So you can check that way. Okay. So let us move on to the next problem. So in this problem, I have considered a three-phase fully controlled bridge converter, which is feeding power to a load which is having a resistance of 10 ohms and a very large inductance to result in continuous constant current with an input from a three-phase supply, which is 415 volts and 50 hertz. Feeder conductors have the resistance of order zero point 0.1 ohms each, and for firing angle of 40 degree, calculate the AC source RMS current in amperes. So again, we are supposed to calculate the AC source RMS current. So let us draw the converter. So this is a controlled bridge converter. So hence alpha. So load is RL load, and the current drawn is constant current, right? R is given as 10 ohms. This is 415 volts and 50 hertz. These feeder conductors have, I'm calling the feeder resistance as RF, which is 0.1 ohms each. Okay. Then firing angle of this converter is 40 degrees, and yeah, that's it. Okay. And we are asked to find the supply RMS current. If IS is the supply current, then IS RMS is to be found, right? So they have told that this current, let us say I naught, output current, right? They have said that this current is constant, but they haven't mentioned its value. So in order to calculate the RMS value of the supply current, first we'll have to calculate this constant current, right? So in order to calculate the constant current, we need to first find the output voltage of this uncontrolled converter. Now for this three phase fully controlled bridge converter, we know that the expression for average output DC is for three phase fully controlled bridge converter. The expression is 3 VML by pi into cos alpha. So if you have issues with the derivation of any of these direct formulas also, you can just give me a heads up so that I'll derive it in the coming sessions. Okay. So this is presented almost all the textbooks also, you can refer from there as well. Okay. Now we know this is where VML is line voltage, right? So we are given, so in the system, let us call Vs as okay, Vs is given as 415 volts, which is the line voltage. So in order to calculate per phase voltage, it will be 415 volts by root 3, right? This is the per phase voltage. and then we can multiply it with root 2 to obtain the peak value because this is line voltage peak value VML. Okay, so you can calculate the average output voltage, and in case you need a reference for this formula, you can just, so this will be, you're integrating from alpha plus pi by 3. So conduction period of thyristors is alpha plus pi by 3 to alpha plus 2 pi by 3 VML sine omega t d omega t. So if you do this, you will obtain this formula. And if you want to get the reference for from where this came, then you will have to draw the waveform. And in case you need my help in doing that, then please let me know. Okay. And then yeah. So using these values, if you put in this formula, I'll do it here. So V naught is the output voltage, which is obtained as 3 VML by pi into cos alpha. When you put the values, it will come out to be 429.33 volts. Then I naught, which is the constant current, can be obtained as V naught by R, which is equals to 429.33 by, and R was 10 ohms, 42.9 amperes. Now we have to calculate the supply RMS. So when you draw the waveform for this converter again, then for this converter, the supply current is constant, right? So it will be constant for 2 pi by 3 period out of pi. So you can directly obtain this as I naught into this, the RMS value. So the waveform for supply current is something like this. And the conduction period is 2 pi by 3. So you know that it's a easy way to calculate here. So you can directly obtain the RMS value using this expression, and then you already know I naught, which is 42.9, and this will be under root 2 by 3. So this will come out to be 35.05 amperes, which is the RMS value of the supply current. Okay, so this was what was asked. Okay, so if you draw the waveform, then it will be much more clear to you, and you won't have to you will directly get this expression by integrating, and this integration limits you will be able to obtain from the waveforms. Now as a continuation of the same question, they are asking if an ideal shunt compensator is used to compensate power factor to unity, then calculate the AC source RMS current in amperes. Now they have asked us that if they are connecting a compensator. Now, when they are connecting this compensator, the current that is drawn from the source will no more be non-linear in nature, right? It will be a sinusoidal current. And since the compensator is providing power factor correction, this sinusoidal current will be in phase with the supply voltage. Power factor correction and compensation. Supply current is balanced and sinusoidal. In this case, the AC source current will be equal to the RMS fundamental active power component of the load current. Because since compensator is supplying all the rest of the part, the only useful part is the fundamental part, right? So therefore, this implies our I source RMS will be equal to RMS of fundamental active power component of load current. So I had already shown you the waveform for the supply current. So in this case, when you do the Fourier analysis, you will have to obtain the waveform, do the Fourier of the waveform. The Fourier of the waveform will be something like 157. Just for your reference, I am writing it, okay? The n pi. So this is the supply current waveform, right? So for this waveform, I will write the Fourier expression here only. So if this peak amplitude is I naught, then it will be 4 I naught by n pi sine of n pi by 3 into sine of n omega t plus phi n. And so this is the instantaneous value, right? So if I want I know that the coefficient of sine is the peak value. So if I want the RMS value, then it will be this peak value divided by root 2. And I want the fundamental RMS, right? So I will take n as 1. 4 I naught by pi, sine n will again be 1, sine pi by 3 by root 2. Because this was the peak value, right? So sorry, root 3. So this will be root 2. That's the peak value. So this will come out to be 2 root 2 by pi I naught into sine pi by 3, which will be equal to root 6 by pi I naught. So this is the RMS value of the fundamental component, right? So the RMS value of the and the active power component can be obtained by multiplying it by with the power factor, right? So, and power factor here is, so here phi n, again I connect here phi n is equals to cos of minus n alpha. So for n is equals to 1 for fundamental component, phi 1 will be equal to cos alpha, which is the power factor. So the active power component will be obtained as IS1 into cos alpha. IS1 was root 6 by pi into I naught. So I naught is 42.93 and cos alpha was 40 degrees. So this I source RMS current can be obtained as 25.64 amperes. Let us move on to the next problem. In this problem, again, a three-phase fully controlled bridge converter is controlled at firing angle of 60 degrees and draws constant current of 30 amperes from a three-phase power supply of 415 volts and 50 hertz. The feeder conductors have a resistance of order 0.5 ohms each. If an ideal shunt compensator is used to compensate power factor to unity, then calculate the ratio of losses in distribution system without and with compensator. So they are expecting us to calculate the ratio of losses in the system without and with compensator, right? So we need to calculate the RMS currents in both cases, right? So using this is a same converter, right? Three-phase fully controlled bridge converter with similar constant current situation. So directly IS RMS expression we can, and this time they have given us the value of constant current, so we don't have to calculate I naught. We can directly so without, if I talk about without compensation, IS RMS. I am taking from the same expressions that derived in the previous question. Okay, under root 2 by 3 into I naught is 30, which will come out to be 24.49 amps. Okay, so the losses in the distribution system will be, since it is a three-phase converter, so it will be 3 times IS RMS square into R feeder. R feeder is 0.5. We will take it each this time. We won't multiply it by 2 because it is a three-phase converter. So we are already multiplying it with 3 here. Okay. So this will give us 900 watts. Now, when we talk about with compensation, then IS RMS is equals to, again, it will be equal to the fundamental active power component, right, of load. Which again, I'm using the same expression that we derived since it's the same converter. Root 6 by pi I naught into cos of alpha. We know I naught is 30 and alpha is 60 degrees here. So this will give us, let me mark a C for after compensation. Okay. So IS RMS C is equals to 11.7 amperes. So loss with compensator will be equal to 3 times IS RMS C square into R feeder. This will come out to be 205.34 watts, and hence the ratio can be obtained as, ratio was as of losses without compensator to losses with compensator. So it will come out to be 900 by 205.34, which will come out to be approximately 4.38. Okay. So let us move on to the next problem. So in this problem, there are three-phase line voltage of 400 volt 50 hertz 4-wire distribution system. Three single-phase loads which are connected between phases and neutral terminals are drawing quasi-square waveform of pulse width 60 degrees, constant current amplitude I of 25 amperes. Calculate the RMS value of the AC main phase current in amperes. So they have asked us to consider a three-phase 4-wire system, right? So let me say this is a three-phase supply, and these are the single-phase loads which are connected to each phase, and let me make it a 4-wire system. This is the neutral connection of the source and the load. So they are saying that the current that the load is drawing is quasi-square wave current. Now, what is quasi-square wave current? This is a standard form of waveform. So this looks something like this. So this is pi to pi, pi to pi, and this pulse width they have mentioned is 60 degrees, and the amplitude is I, and the value of this I is 25 amperes. So this is the current I that the system is drawing. Okay, and this is a 400 volts 50 hertz system, and they have asked us to calculate the RMS value of this phase current. So we know that the expression for I RMS is 1 by T integral I of T square dt, right? And integration, right? So here I is constant current, right? Which is, I can say, capital I d omega t from the interval of pi by 3 to 2 pi by 3. In rest of the interval, this current is 0. So this term will anyways become 0. And the time period is pi. Okay. Square root of this. So when you solve this, you will obtain IDC into IDC by root 3. Sorry, I by root 3. I is the constant term. And I is already given as 25 amperes by root 3, which is equal to 14.4 amperes. So in this kind of expression, like whenever you have a square wave, this can be called as a subcategory of square wave, right? So when you are asked to calculate the RMS value of this kind of square wave, you can directly write this, and the amplitude is constant. So you can write constant amplitude under root of period for which this pulse is conducting. So this is here pi by 3, right? and total time period, which is pi. And why I am taking pi as a total time period? Because in RMS and the expression of RMS, when we take a square, then all these negative will come and positive, right? Then it will be, then when I square this, it will be like this, right? It will be same. So I can directly take time period as pi instead of taking as 2 pi. Even if I take 2 pi, the result will come as same only. It won't be different, but it is easier. So that is why we do this. So you can directly write it this way. So this will give you directly I by root 3. This is like a simple, simplification instead of writing the whole formula. So once you are through with this formula, you will be able to see this form directly. Okay. So it will save some time. So this is the same method that I use here also. This, right? This. So 2 pi by 3, it was conducting for 2 pi by 3 out of pi interval, like this waveform, right? It was conducting for 2 pi by 3 interval out of pi. So again, after squaring, this also will come up. Okay. So I can directly use up to pi and then I can use this expression. Okay. So you can also try using this expression. Now, in the second part of this, they have asked us to find the RMS value of the AC main neutral current. So in this, there will be neutral current, right? This is the source neutral, NS. This is the load neutral, and there will be a neutral current flowing in this conductor. So in order to find the neutral current, let us use waveforms. So if you look at, let me call the three phases as IS, A, B, and C phases. And if this is ISA, this is my quasi square wave current. So this is pi to pi. Each interval is of 60 degrees. So I am making the dashed lines after every 60 degrees, since the pulse width is 60 and 180 by 60 will be 3. So from pi to 2 pi, there are 3 intervals. And why am I making these dashed lines? Because the phase B and C waveforms will be phase shifted by 120 degree, right? So since each width of dash line is 60 degrees, so I have to shift 2 dashes, right? So now let me draw the waveform of ISB. So ISB will be 120 degrees from this. So ISA was starting from here, 60 and then 120. So ISB will start from here. Then after after two gaps, after two gaps, right? And then again I will make ISC, that will be 120 degrees shifted from B phase. So since B was starting here, ISC will start here, right? Okay. And when you add all these waveforms, so we know that neutral current is equals to ISA plus ISB plus ISC, right? In the three-phase four-wire system. So the neutral current waveform will be obtained something like, these are all time axes, you all know that. This is I neutral. So when you add all these three currents, then you will obtain the waveform of neutral current as something like this. You can do these in simulations also, instead of doing it manually. Yes, Suresh sir, you can directly ask your doubt. Yes, already like your attendees list will be recorded with me, and so this course, yes. NPTL, in order to take this certificate from NPTL, you have to give an exam. So once you give an exam based on, you have to register for the exam and then appear for the exam. So after giving that exam, you get the certificate. Okay, so if you want the certificate, you have to solve the assignments properly. All the assignments mark are added along with the final exam marks. So there is a proper distribution, and then you can obtain the certificate with the marks that you have obtained. Okay. And if somebody has raised the hand, they can directly ask doubt if they want. So yeah, so this is the yeah, expression for neutral current, and we know the maximum amplitude is 25 amperes. This will be minus 25 ampere. So when you calculate the RMS value of this waveform, it will be 25 amperes. We can say directly that we can directly say this from the waveform, because when I will square this I neutral waveform, then it will come out to be something like a constant DC, right? If I square it, it will come out to be it will become a constant DC with 25 square as magnitude. So RMS value can be directly told as 25, right? You can try finding the formula, and then you will understand the physical analogy as well. So the RMS neutral current is 25 amperes, hence found. Okay. So let us move on to the next problem. So in the next problem, in a three-phase line voltage of 415 volts and 50 hertz system, four-wire distribution system, three single-phase loads, again the same system, having a single-phase thyristor bridge converter drawing equal 20 ampere constant DC current at 60-degree firing angle of its thyristors. Calculate AC source RMS current. Again, we are calculating the IC source RMS current, but this time, instead, along with the single phase loads, they have added uh, a single phase thyristor bridge. That is, they have made the load as non-linear. So they've asked us to calculate the source RMS current. So due to the connection of single phase bridge rectifier, we already saw the waveform, right? So in the waveform, if we have a single bridge rectifier, and there is some load, and it is supplying a constant current of 20 amperes, right? Then I can draw the waveform as Vs. If this is Vs, this is Vs, and if this is Is, then if this is my alpha is my triggering angle, then this is pi plus alpha, and this is pi, right? Then my supply current will be from this time to this time, right? It will be positive in this interval from alpha to pi plus alpha, and then it will be negative in the up to this interval, 2 pi plus alpha, right? So this will be the waveform. So when you have this waveform, they have asked us to calculate the RMS value of the supply current, right? Now it becomes very simple now, because we know that this is again a variant of square wave, and when we square it, it will come out to be a DC of this fixed amplitude, and this fixed amplitude is given as I naught, which is 20 amperes. So again, the supply RMS current becomes 20 amperes, right? So just the waveforms, that's it, nothing else needed. So in the same question, they have asked, if an ideal four-wire shunt compensator is used to compensate power factor to unity in each phase, then calculate the source current. Then what will be the difference in the source current? So again, when we add the compensator, the new supply RMS current with compensator is equals to the fundamental active power component of the load, which is equal to, so for this, it will be 2 root 2 by pi into I naught into cos alpha. So we have done that for three phase before. If you do the similar analysis for this single phase uncontrolled converter, then you will obtain this expression. So I'll just briefly write the expression for Fourier series expression for you to understand. So this is the waveform, okay, and for its Fourier series, I am writing, okay. So Is is equals to summation of n odd values 1357 continue till infinity 4 I naught by n pi sin of n omega t plus phi n. So the peak value is 4 I naught by n pi, right? So the RMS value is, we will divide it by root 2. So it will become 2 root 2 I naught by pi. For fundamental, okay, it's n. So Is 1 RMS will be equal to 2 root 2 I naught by pi, right? So this is Is1 into cos alpha. Okay. This is 2 root 2 by pi. I naught was 20 amperes, right? And alpha was 60 degrees. So this will come out to be 9 amperes. Now the initial current was 20 amperes, which is reduced to 9 amperes because we have added the compensator. So this is the advantage of, like, the benefit of adding the compensator to the system. Let us move on to the next problem. So in the next problem, again there is a three-phase supply with a line voltage of 415 volts and 50 hertz, and it is a four-wire distribution system again. And this time they have three single-phase loads between phases and neutral, having a single-phase thyristor bridge drawing equal 10 ampere constant current at 45-degree firing angle of its thyristors. Feeders and neutral conductor have a resistance of order zero point 0.5 ohms each. If an ideal shunt compensator is used to compensate power factor to unity, then calculate the ratio of losses in the distribution system. Again, we are asked to calculate the ratio of losses in the distribution system. So in order to calculate the ratio, we know that we need to calculate powers with and without, right? So in this case, like previous, this is the same system like the one in the previous problem. So we can obtain so we can have two partitions without compensator and with compensator. So without compensator, if I say, then the RMS current will directly be equals to 10 amperes. You've already seen this. And the neutral RMS current will also be equals to 10 amperes. So losses without compensator will be equal to 3 times I supply RMS square into R feeder plus I neutral RMS square into R feeder. So neutral current is also there, and that conductor also has resistance. So we have to add this term. So this will be 4 into 10 square into zero point 0.5, which is equals to 200 watts. Now, if we think about with compensator, then again, since it's the same system, we can directly use the equation that we have. So the new supply current will be the fundamental active power component of the load again. And the expression is Is1 into power factor, that is cos alpha. So Is1 for this converter is 2 root 2 by pi into I naught. So this angle is 45 degrees, which will come out to be 6.366 amperes. And losses with compensator will come out to be, since we have used compensator, so neutral current will become 0. Because all the three-phase currents are balanced and sinusoidal, the neutral current will become 0 now. So the losses will only be in the phases. So it will be 3 times I supply nu square into R feeder, which is 3 times 6.37 square into zero point 0.5, which is 60.87 watts. So the ratio that was asked is without by with, which will be equal to 200 by 60.87, which is 3.29. That means we get an advantage of approximately 3 times if we use the compensator in this system. Our power loss will reduce by 3 times. That is an advantage that we'll get when using the system. So whenever we have any kind of system, before directly putting any kind of compensator, we do this analysis. And if this figure is good enough for us in lieu of the cost that we are paying for the compensator, because compensators are not cheap, right? They are costly. So if they are able to justify the cost, if this factor is sufficient for us, then only we go for the compensator. So these are the last set of problems, just two more. So in this problem again, it's a three-phase system with a line voltage of 415 volts and 50 hertz. It's a four-wire distribution system. And again, a single phase load is connected. This time the load is having a 75 amperes current it is drawing at 0.85 lagging power factor. And the feeders and the neutral conductors have a resistance of 0.1 ohms. Calculate loss in the distribution system. So the system is something like this. It's a three-phase supply, the R, Y, and B phases. And load, only one load is connected between phase and the neutral. This is source neutral, and this is load neutral. This is load, okay? And other two phases, nothing is connected. And the load is drawing 75 ampere current at 0.85 lagging power factor, right? And this feeder resistance given as 0.1 ohms. So in this case, supply RMS is equals to 75 ampere, and neutral current RMS will also be same because same current is flowing through both supply and the neutral, right? So losses will be equal to 2 times because it is in one in this R line and the neutral. So it's 2 times. Both the currents are same, right? So we can directly write it. IMS is square into R. 75 square and R is 0.5, sorry, 0.1. So the losses will come out to be 1125 watts. Now this was without compensator. Now in the next part, if an ideal 4-wire shunt compensator is used to compensate power factor to unity in each phase, then calculate the losses in the distribution system. Now, initially with unbalanced load, so this is an unbalanced load. This is an example of an unbalanced. Only load is connected in the R phase and Y and B phase are not at all loaded, right? So if you look at this example, then this is an unbalanced system. Now, if you add a compensator to this, I haven't shown adding any compensator in any system. Wait, I just show here. So if this is my system, I'll draw it again. This was my only load and both were open, right? This is my neutral and it is connected like this with the load, right? Now, when I say that I'm connecting the shunt compensator, what I am actually doing is I'm connecting a block this. I'm connecting this block with all the four or all 4 points, that is R, Y, B and N. So this is my shunt compensator. So after connection of the shunt compensator, what is happening is my current is becoming balanced, and now the new supply RMS current with the compensator is IS1 into cos of theta that we have seen so many times. So IS1 here will directly be when I am balancing the system. This is a load supply load current. So load current will directly become 75 by 3. Why? Because initially this current the load was consuming 75 amperes. Now after balancing the system, this after balancing, my system would be equivalent to this, and each phase will be taking 75 by 3 amperes current. This is the advantage of, so it won't change physically, but when we look from this side, when we look from the source side, right, then our system will look like that. When we look from this side, so then our system will look then our source won't realize that it's a unbalanced current because of the uh, together shunt compensator and load together are behaving like this. They both, right? This is the red line here. So because of the addition of shunt compensator, our system is behaving like this, right? So this is a good system because this is a balanced load. Initially, the load was unbalanced. Okay, so this is my IS one will be 75 by 3, and the power factor is directly given as 0.85. So the new supply RMS current comes out to be 21.25 amperes. So initially it was 75, now it's only 21 amperes, right? So let us see what are the losses now. Losses with IS RMS square into R feeder, which is equals to 3 into 21.25 square into 0.1, which is equals to 135.47 watts. So you see the difference, right? Initially it was initially it was 1025 watts, and now it has reduced to only 135 watts just because we had put this compensator here, right? So this is the advantage of this compensator. So you can directly look at these numericals and understand the significance of adding this compensator to the system. Then only you will realize the importance and of the system, right? So these are all the questions that I have prepared for you guys for today. Okay. So in any of these problems, if you have any doubts, please you can unmute yourself right now and ask. And if you have any other doubts overall in any kind of discussion or any point that we have discussed today, then also you can ask. And if you have any suggestions for the next tutorial session, and also you can give me any kind of feedback that you have, if I am too fast or if you want me to cover less examples and more theory, or more, or vice versa, whichever kind of, please feel free. So as again, see, I'll be here for 2 hours every week. So if I'm here, I would like to be helpful to you guys, for helping you out in whichever you need. So you can directly give me a very frank feedback. Don't worry about it. And then I'll try to give my best efforts so that I can help you out, guys, with the in a smooth execution of this course.
Madam, myself Venkat Narayana.
Yes, sir, please.
Madam, you are unable to type that only have to write only true value, madam. Real value, unable to write that polar form or total rectangular value, madam. In single point questions, madam.
In
In
single, yes, yes.
uh,
So
you
they are
are you.
asking you for the magnitude only. So whenever
Oh, okay,
you have to write only the magnitude. In polar form, when you convert, the magnitude you get, right? So only that magnitude you have to write in those questions.
okay. No need to write that angle and
Yes, yes.
imaginary part, madam.
Yes,
Yes.
yes, angle is not needed. So you in
Okay.
Cartesian form, if you will write, so if your answer will be in A plus IB form, right? And if you convert,
Okay.
then it will in polar form, it will be R angle theta. So if they are not asking you angle separately, then you have to write the value of R. Okay, that is the magnitude.
Okay. Okay.
Okay,
Okay. Thank you, madam.
okay, welcome, sir. Anybody has any other questions? Okay, guys, then the recording this course books are helpful to start learning. Okay, Satish, you can refer Bhim Singh sir's book. So the tutor of this course, Bhim Singh sir, he has his own book. So he has a lot of numerical examples there, and the material is literally parallel. So whatever sir is teaching in the class is written in his book in a literal manner. So you can use the Bhim Singh sir's book. That is what I will recommend as of now. And if you need anything specific in any kind of resources or any other lectures, then you can let me know that specific topic so that I can point you out. And if you're new, then don't worry. So we have taken this course from the very basic. You can just go through the tutorial session and the NPTEL videos and refer to the book. And in case you have any doubts, don't worry which kind of doubt it is. You can ask we can have a discussion here. Okay, just tell me what kind of doubt it is, and we will discuss here. Okay. And yes, I told you that I'll be showing a simulation to you guys. Wait, I'll just okay. I don't have the simulation right now with me. Wait, I'll add it in my next slides, okay? In the upcoming session, I will add the tutorial sheet that I have made. So I'm using MATLAB and I'm using MATLAB editor for simplifying my computation. So I have made a simple script, MATLAB script for for converting the three-phase components into symmetrical components and vice versa. So if you are interested in that, then we can discuss that also. It will be helpful for you. So if you when you write or code something, it simplifies your computation procedure and it gives you a very clear thinking. Okay. So if you are interested in that, then we can discuss that as well. And you can do the simulations in Simulink. If you had any kind of doubts in any of these converters, you can just put these switches and everything in Simulink, and then you can try it out. Okay. Okay, guys. Then we'll end today's session. Thank you for attending. If you have, I'll just 1 minute. I'll share. I'll write my email ID in the chat box. If you have any doubts, you can post there, or any doubts or anything that you want me to teach in the next session. So you can just mail me at this ID. Yeah. So I have posted my email ID in the chat box. In case you have any suggestions or any kind of feedback, please feel free to give feedback. I want to be helpful for you guys. Okay, so you can tell me there. Okay, okay. Thank you guys. So I'll end today's session then. Have a good day. Bye bye. Have a good day. Bye bye.